In an off-grid system, the neutral serves as a reference point for electrical potential. It is typically connected to ground for safety and to stabilize the system's voltage. Since there is no connection to a utility grid, the neutral has to be created. There are several options to consider. Firstly, a ground grid can be installed. This involves burying a grid of copper or galvanized conductors around the location. Ensure the grid is at least 2 feet deep and spaced approximately 6 feet apart. The neutral bus bar of the inverter should be connected to this grid. Secondly, a concrete encased ground rod is another option. Drive an 8-foot or longer ground rod into the earth. Encase the rod in concrete to improve conductivity and stability. Connect the neutral bus bar to the ground rod. Thirdly, grounding to a well pipe might seem like an option, but it is generally not recommended due to safety concerns. If you do decide to go this route, connect the neutral bus bar to the well pipe, ensuring the pipe is made of conductive material and is properly connected to the ground. Fourthly, a driven ground rod can be used. Drive a ground rod into the earth as deep as possible, ideally at least 10 feet. Connect the neutral bus bar to this ground rod. Fifthly, consider grounding to a water source. If there is a nearby body of water such as a pond or lake, the neutral bus bar can be connected to a submerged metal plate. When considering these options, several additional factors need to be taken into account. Soil conditions can greatly affect the effectiveness of the grounding system. Shale soil, specifically, can be problematic due to its resistivity. It is recommended to use a soil conductivity tester to determine the soil's resistivity. Aim for a ground resistance of less than 10 ohms. Use a multimeter to test the resistance between the grounding system and earth. Multiple grounding points should be considered to improve redundancy and overall reliability. Safety is paramount, so always follow proper electrical codes and consult with a qualified electrician to ensure the system is installed safely and effectively. Remember that the neutral is a crucial part of an electrical system, providing a return path for current and helping to maintain a stable voltage. In a grid-tied system, the utility provides this neutral connection. In an off-grid system, it is up to the system designer and installer to create this neutral. When selecting a grounding method, consider factors such as soil conditions, local electrical codes, and safety requirements. The ground grid is an effective method, especially in areas with poor soil conductivity. It provides a large surface area for contact with the earth, which helps to lower ground resistance. The concrete encased ground rod can also be effective, as the concrete helps to improve the contact between the ground rod and the surrounding soil. Driving a ground rod as deep as possible is generally a good practice, as this will help to reach more conductive soil layers. Grounding to a water source can be effective if the water source is in good contact with the earth. However, it is important to ensure that the metal plate is properly submerged and protected from corrosion. Regular maintenance is essential for any grounding system. Inspect the grounding connections regularly to ensure that they are tight and free from corrosion. Test the ground resistance periodically to ensure that it is within acceptable limits. If the ground resistance is too high, take steps to improve the grounding system, such as adding additional ground rods or improving the soil conductivity. The system neutral is connected to the grounding electrode conductor, which in turn connects to the grounding electrode, such as a ground rod. The purpose of grounding is to provide a low impedance path for fault current to return to the source, which helps to trip a circuit breaker or fuse and to energize the circuit. This protects people from electric shock and prevents damage to equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in the National Electrical Code, also known as NEC. NEC Table 250.66 provides guidance on sizing the grounding electrode conductor for alternating current systems. For example, if the service entrance conductors are 2/0 American wire gauge, also known as AWG copper, the grounding electrode conductor should be at least number 4 AWG copper. The grounding electrode should be a listed and labeled ground rod that is at least 8 feet long and 5/8 inch in diameter. It should be driven into the ground until at least 8 feet of the rod is in contact with the soil. If the soil is rocky or difficult to penetrate, the ground rod can be buried horizontally in a trench that is at least 30 inches deep. Alternatively, a ground plate can be used instead of a ground rod. A ground plate should be at least 2 square feet in area and made of copper or other corrosion-resistant material. It should be buried in the ground at least 30 inches deep. In addition to the grounding electrode conductor, there is also an equipment grounding conductor which connects the metal enclosures of electrical equipment to the grounding system. The purpose of the equipment grounding conductor is to provide a low impedance path for fault current to return to the source, which helps to trip a circuit breaker or fuse and to energize the circuit. This protects people from electric shock and prevents damage to equipment. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device, such as a circuit breaker or fuse, that protects the circuit. NEC Table 250.122 provides guidance on sizing the equipment grounding conductor. For example, if the overcurrent protection device is rated at 20 amps, the equipment grounding conductor should be at least number 12 AWG copper. The equipment grounding conductor should be run with the circuit conductors in the same raceway or cable. It should be connected to the metal enclosure of the electrical equipment using a grounding screw or lug. It is important to note that the neutral conductor and the equipment grounding conductor should be kept separate. The neutral conductor carries normal load current, while the equipment grounding conductor only carries fault current. Connecting the neutral conductor and the equipment grounding conductor together can create a ground loop, which can cause unwanted current to flow through the grounding system. This can lead to nuisance tripping of circuit breakers and can also create a shock hazard. In addition to the grounding electrode conductor and the equipment grounding conductor, there may also be a bonding conductor. A bonding conductor is used to connect different metal parts of the electrical system together, such as metal water pipes, metal gas pipes, and metal building frames. The purpose of bonding is to create a common ground potential throughout the electrical system. This helps to reduce the risk of electric shock and prevents damage to equipment. The size of the bonding conductor is determined by the size of the service entrance conductors. NEC Table 250.102 provides guidance on sizing the bonding conductor. For example, if the service entrance conductors are 2/0 AWG copper, the bonding conductor should be at least number 6 AWG copper. The bonding conductor should be connected to the metal parts of the electrical system using bonding clamps or lugs. It is important to ensure that all bonding connections are tight and free from corrosion. Grounding is a critical part of any electrical system. It is essential to ensure that the grounding system is properly designed and installed to protect people from electric shock and prevent damage to equipment. Always follow proper electrical codes and consult with a qualified electrician to ensure that the grounding system is safe and effective. When dealing with shale soil, which is known for its poor conductivity, special attention needs to be paid to the grounding system. Firstly, consider using multiple ground rods spaced at least 6 feet apart and bonded together. This will help to increase the surface area in contact with the earth and lower the overall ground resistance. Secondly, chemical ground rods can be used. These ground rods contain chemicals that leach into the surrounding soil, improving its conductivity. However, it is important to follow the manufacturer's instructions carefully when installing chemical ground rods, as they can be corrosive. Thirdly, soil amendments can be used to improve the conductivity of the soil around the ground rods. For example, bentonite clay can be added to the soil to help retain moisture and improve conductivity. Fourthly, consider using a ground grid, which consists of a network of interconnected conductors buried in the earth. A ground grid can be very effective in areas with poor soil conductivity, as it provides a large surface area for contact with the earth. Fifthly, the concrete encased electrode, also known as a U for ground, is another option. This consists of a length of bare copper conductor encased in concrete. The concrete helps to protect the conductor from corrosion and also improves its contact with the earth. Sixthly, ensure that all grounding connections are tight and free from corrosion. Use corrosion-resistant connectors and protect the connections from the elements. Seventhly, regularly test the ground resistance to ensure that it is within acceptable limits. If the ground resistance is too high, take steps to improve the grounding system. Eighthly, consult with a qualified electrician or grounding specialist to ensure that the grounding system is properly designed and installed. They can perform a soil resistivity test and recommend the appropriate grounding methods for the specific site conditions. Ninthly, documentation is key. Keep detailed records of the grounding system, including the location of ground rods, the size and type of conductors used, and the results of ground resistance tests. Tenthly, when connecting dissimilar metals, such as copper and galvanized steel, use dielectric connectors to prevent galvanic corrosion. 11thly, in areas with very poor soil conductivity, it may be necessary to install a supplemental grounding system, such as a plate electrode or a deep-driven ground rod. 12thly, consider using a surge protective device, also known as SPD, to protect sensitive electronic equipment from voltage surges. An SPD should be connected to the grounding system to provide a low impedance path for surge current to flow to ground. 13thly, always follow the manufacturer's instructions when installing grounding equipment. 14thly, be aware of any underground utilities in the area before driving ground rods or excavating for a ground grid. 15thly, use appropriate personal protective equipment, also known as PPE, such as gloves and eye protection, when working with grounding equipment. 16thly, never work on electrical equipment while it is energized. Always de-energize the equipment and verify that it is de-energized before working on it. 17thly, be aware of the potential for stray voltage in the grounding system. Stray voltage can be caused by unbalanced loads or by ground faults. If stray voltage is present, it can create a shock hazard. 18thly, regularly inspect the grounding system for signs of damage or corrosion. Replace any damaged or corroded components immediately. 19thly, consider using a ground fault circuit interrupter, also known as GFCI, to protect circuits that serve outdoor outlets or other locations where there is a risk of electric shock. 20thly, use a ground resistance tester to measure the resistance of the grounding system. A ground resistance tester is a specialized instrument that can accurately measure the resistance between the grounding system and earth. 21st, ensure that the grounding system meets the requirements of the National Electrical Code, also known as NEC, and any other applicable codes and standards. 22nd, the NEC requires that all electrical equipment be properly grounded. Grounding is the process of connecting electrical equipment to the earth. This provides a path for fault current to flow back to the source, which helps to trip a circuit breaker or fuse and to energize the circuit. 23rd, grounding is essential for safety. It protects people from electric shock and prevents damage to equipment. 24th, a properly designed and installed grounding system is a critical part of any electrical system. It is essential to ensure that the grounding system meets the requirements of the NEC and any other applicable codes and standards. 25th, consult with a qualified electrician or grounding specialist to ensure that the grounding system is properly designed and installed. They can perform a soil resistivity test and recommend the appropriate grounding methods for the specific site conditions. Grounding is a complex topic, and it is important to have a thorough understanding of the principles of grounding before attempting to install a grounding system. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work.